Hello everyone, welcome back to class. Today we are going to start on our next group of neurotransmitters. These are neurotransmitters known as monoamines, and we are actually going to spend today and Friday talking about catecholamines. Okay, so within monoamines there's a group called catecholamines. So what are monoamines? First of all, they are just a group of neurotransmitters that share a common single amine group. Okay, so these are all monoamines: dopamine, norepinephrine, epinephrine, and serotonin. These are the monoamines. Now, within the monoamines, there are catecholamines, which is dopamine, norepinephrine, and epinephrine. So pretty much all monoamines are catecholamines except for serotonin. So norepinephrine and epinephrine are also known as noradrenaline and adrenaline in this course. Okay, now particularly their roles as peripheral hormones, that's when we usually talk about noradrenaline and adrenaline is their role as hormones. When we're talking about the neurotransmitters, then it's norepinephrine and epinephrine. Okay, but in this class we can kind of switch back and forth. That's okay. In other courses, see what your profs want. Now we're only going to we're only going to really focus on norepinephrine or noradrenaline in this class, because this is the one that functions in the central nervous system more, whereas epinephrine or adrenaline is mostly in the peripheral nervous system, so we don't really talk about it much, okay? Now, any nerve that secretes norepinephrine is what we call noradrenergic cells, so that's why I go ahead and say for this class you can call norepinephrine noradrenaline, because they are noradrenergic cells. So it just simplifies it, okay? But for today we are going to focus on dopamine. Okay, so dopamine, really just one name. You've probably heard about it. We mentioned it a little bit in the last class when talking about the role of acetylcholine in Alzheimer's, and how it's the balance between acetylcholine and dopamine in the early stages. So again, you should be familiar with, you've probably at least heard of all of these neurotransmitters before. So what makes up a catecholamine? Catecholamines all have a common structure. They all have this catechol nucleus and an amine group. Obviously, it will vary. So if we go back to the slide, we can see that catechol nucleus in these three. And you can see why serotonin is different. So it's missing that extra OH over here, which is what makes it slightly different. But all of these do have that amine group, okay? Which is what makes them monoamines, because they have one amine group each. Obviously, in the last slide, it also showed the differences of how you can combine these two. So, all of these catecholamines are going to be synthesized kind of in a group, okay? They're synthesized from each other. So this is one large slide, one large diagram of the synthesis. Do you need to know all of it? Pretty much yes. You're going to need to know where we start, how we get to dopamine. Once we learn norepinephrine in the next class, you're going to need to know how to synthesize norepinephrine, okay? The synthesis of epinephrine isn't going to be as important. It's definitely these first two, obviously, that you're going to need to know the most. But here is the synthesis, okay? So it's really just one biosynthesis of all catecholamines. And so the main thing here is we're going to start with dietary L-tyrosine, and then using tyrosine hydrolase, or TH. It's an enzyme that's going to turn that into L-dopa. Okay, again, you can just use L-dopa, just use TH. Even in the midterms, you can go ahead and use the abbreviations. Go for it. Now, tyrosine hydrolase, or TH, is a rate-limiting enzyme, so it's very important in the synthetic pathway. And it's the site of regulation of both dopamine and norepinephrine synthesis. So if we alter the function of tyrosine hydrolase, it will disrupt the synthesis of our catecholamines. So here we have a drug AMPT, which is alpha-methyl paratyrosine. Not that you really need to know that. But it's a drug that inhibits the activity of tyrosine hydrolase. So it depletes both dopamine and norepinephrine. Don't worry, we'll talk about this more in other slides. But one thing I may ask in the midterm is, here's the, tell me about the synthesis, and then tell me one drug that could disrupt it. Okay, and so AMPT would be an example. And you'd have to tell me where it works. Okay, so far we've gotten from L-tyrosine to L-dopa via tyrosine hydrolase. Then L-dopa is turned into dopamine via dopa decarbylase. Okay, so you can see kind of where things are coming off. Decarbylase, we removed that, and now we've got dopamine. Beautiful. So that is our first catecholamine. That's the one we're going to talk about most today. From dopamine, if you use DBH, or dopamine beta hydrolase, it turns dopamine into norepinephrine. Okay. So again, you do need to know that. Do you need to know the structural change? No. You just need to know the names of everything, and all of these different enzymes. Okay. From norepinephrine, PNMT turns it into epinephrine. Okay, so that is phenylethylamine and methyltransferase. It's a long name. Again, just use the acronym, guys. It's so much easier. So PNMT turns norepinephrine into epinephrine. Now, the big ones here is you're going to need really L-tyrosine plus TH equals L-dopa. L-dopa plus dopa decarbylase equals dopamine. Dopamine plus DBH equals norepinephrine. You can kind of stop there. So we now have the synthesized dopamine in our in our presynaptic cell, or norepinephrine, either one. But we now need to transport our synthesized neurotransmitter into vesicles. So we do that using VMAT. VMAT. This is the transporter that loads dopamine into the synaptic vesicles. Okay. So VMAT is for dopamine. We'll talk about in the next lecture about norepinephrine and what its transporter is called. Now, there is a drug called reserpine that inhibits VMAT, and what that does is it depletes dopamine and norepinephrine because it gets broken down if dopamine or norepinephrine is just hanging around in the cell and not in a vesicle. So reserpine treatment can then cause sedation or depression in humans, and that's really because we get a depletion of dopamine, norepinephrine in those synapses, and then they can't go on and do their stuff. Okay, so now what about the metabolism of dopamine? How do we break it down? You'll notice we're following a similar format to the beginning of the acetylcholine lectures where we talk about synthesis, the vesicles, and then now breaking it down. So there's two different pathways in which dopamine can be metabolized. So we always start with dopamine. Now there's an intracellular pathway, so within this cell, obviously, and an extracellular pathway. So the intracellular pathway, then dopamine gets broken down using monoamine oxidase, so MAO, or it can be broken down with aldehyde dehydrogenase. So there's two options. Monoamine oxidase works on all monoamines. Aldehyde dehydrogenase is a little bit more specific, but either one will break dopamine down into DOPAC. So DOPAC is 3,4-dihydroxyphenylacetic acid. That's why we call it DOPAC, way easier, okay? This is an intermediary step. It is then broken down, again, using COMT. Okay, so COMT is very common. You should know what COMT is. Read it here, learn it, memorize it. Hint, hint. So COMT is catechol O-methyltransferase, and it turns DOPAC into HVA. Okay, so homovinylic acid. Now, the extracellular pathway is very similar to the intracellular pathway, except we use the enzymes in reverse order. So extracellularly, then we're going to use COMT first on dopamine. And when you use COMT first, you end up with 3-methoxytyramine, or 3-MT, and then you'll break that down with monoamine oxidase or aldehyde dehydrogenase, and again, you'll end up with HVA. Okay? So the pathways, they use the same enzymes, it's just which order do you use those enzymes. And then because you're using the enzymes in different orders, you're going to have different intermediary products. Okay? So know which order the enzymes go in each pathway and know what the final product is. So HVA is named because it is very similar to vanillin, which is that aromatic component of vanilla. So you can kind of remember that, maybe think about how dopamine or vanilla, when you're making cookies, they smell good. It's usually the smell of vanilla makes me happy. Dopamine makes you happy. Dopamine, you end up with vanilla. I don't know. That's just how I remember it. Might be roundabout, but it helped me. So, we have now talked about the synthesis, the dopamine moving into the vesicles, and then the dopamine being broken down, and how it can be broken down intracellularly or extracellularly. Well, how does the dopamine get back into the presynaptic cell? That is via the dopamine transporter. So the dopamine transporter is called DAT, D-A-T. Okay? And so DAT, again, it's a transporter, so it takes dopamine from the synapse and brings it back into the presynaptic cell where it can then be broken down. Great. Well, this is the area where cocaine and other amphetamines affect the cell, okay? So what they do is they inhibit DAT. So by inhibiting the reuptake of dopamine, it allows the dopamine to stay in the synapse longer, which means the dopamine can bind to the receptor on that postsynaptic cell longer or more, and that leads to hyperactivity of the dopaminergic system. Okay? So we've got synthesis in the presynaptic cell. We've then got the dopamine being moved into the vesicles using VMAT. Dopamine, or the vesicles, will be bound to the presynaptic cell membrane. dopamine's released, binds to the dopamine receptor on that postsynaptic cell. It can then be taken back up by DAT and then broken down intracellularly. Or you can kind of see here some of this dopamine is kind of floating away to the side, and that's because that dopamine is going to be broken down extracellularly. Okay, so that is the role of dopamine within that synapse. That's how it works. Great. Okay, so again, here is the dopaminergic synapse. Really know this. Tyrosine, we get, some of it from our diet. It comes in, turns into dopa, turns into dopamine. VMAT puts it into the ventricles. The ventricles then bind. Dopamine's released, and it can bind to receptors on that postsynaptic cell or the presynaptic. We'll talk about that. And then there's the dopamine transporter, or DAT, where stuff gets taken in. Okay, you need memorize this cell, or this. Well, yeah, but this figure, this whole thing, you need to know it. Okay. You also want to know, we talked about where things can be interrupted. Okay. So let's end this video here, and in the next video, we'll start talking about the dopaminergic receptors and how that plays a role in the dopamine systems.